ahead and look at 11.5 on page 86. So again, here's our equations. We're going to start using these equations, I think, right here. Here we go. So in this case, we're going to be using one of these two forms. If we have one or two objects that rotate and have a collision, we're going to use this one. An example of that is shown right here. This object's rotating, another one collides with it. That's this first form, okay? There's this red form right here. If you have a rotating object that changes shape, maybe you're not sure what I mean by that. That's right here. This one. You have a neutron star where it collapses. So we're going to do both of these, all right? So let's clear out those annotations and start looking at this thing. Okay, whoops, we're doing this one, all right? And then don't forget, if you ever have a point mass, you can use that trick. All right, great. Okay, so you have a turntable rotating. So imagine you've got this disc that's spinning. And so to be clear, this is the turntable that's rotating, this thing here, this red object right here, okay? That's our turntable, the red object. It's a uniform disc, mass M and radius R. And then you have a thin ring with identical mass and radius. So it's also got the same, and we're going to drop it on top. So both of these have mass capital M and radius capital R. Got it. Okay, and the turntable is rotating with 10 RPMs. Think to yourself, 10 RPMs, what is that variable? Hopefully it makes sense that it's this. Okay, so omega naught, that's the RPMs, or the initial angular velocity, okay? Now heads up here, to be clear, shouldn't we really be using vectors? Of course, L initial equals L final vector. So I want to be clear about something here. However, I'm going to assume that this is the z-axis, or k-hat. And so now we could just stick on any, like the turntable is initially rotating, I think, negative k-hat according to the picture, right? But yeah, so in physics class, sometimes we'll flip that. So we'll take a look at the solutions in a minute and see if I remember to do that. All right, so here, hopefully you caught this. That's just convert, you multiply, and it should be off by a factor of 10. So we have revolutions per minute. That's what an RPM means. So let's go take a look at that conversion and see if that's good. All right, so there's our conversion. And now notice I didn't include the vector here. So I got a little bit lazy. So this is the speed, and then the vector would actually be negative, right? So my apologies for that. I'll put a note here in my... Okay, got it. Now, in this case, oh, it says my screen sharing is paused. All right, there we go. Oh, whoops. Okay, I shared the wrong button. Let me get the right screen sharing. Sorry about that. I hit the wrong screen share button, so now see that. Sorry about that. So there's the conversion factor, and notice I left off the minus sign. So okay, great. Evidently, part B means take a guess. So let's go take a look. All right, so let's guess. You're rotating at 10 RPMs. After this thing collides, you got the same mass. Do you think it'll be 5 RPMs, bigger than 5, or less than 5? Will it be 5, bigger than 5, or less than 5? Kind of go with your gut, okay? And where'd that chat go? Somewhere. All right, I lost my chat, so I can't see it, so I'll go back to there in a second. So now let's calculate the final rotation rate. Oh, okay, and so we're just getting the rate, so that's cool. That means we don't have to worry about the plus minus. But so in this case, we're going to use this equation. Oh, there my chat popped up. Okay, let's take a look. Yeah, Jay, it's negative because it's rotating with the axis that way. So, yep. Whoa, come on. Got to move this out of there. Then I can click this. All right. So we're trying to use a problem like this. Rotating, we know the moments of inertia because we know the mass and the radius and the shape of each, right? So we know I1 and I2. This one, I'll call omega 2 initial, is not initially rotating, right? So that's going to take care of this one right here. And then they have the same final because it's perfectly inelastic, as I believe Sam was talking about. Okay, so it's this equation. We know this number, we know this number, we know this, and we know that these two are the same. I should be able to get omega final. Let's try that and go over and look at it and see what I did. Okay, here's the problem. Now, object 2 is not initially rotating, so that one's going to drop out. That drops out. So I1, omega 1, and now we get this result. It looks just like momentum. The only difference is, look at this. Notice there's no 1/2 there. That is the ring, okay? The ring, because all the mass is at the outside, doesn't have that have that 1/2. And notice this is less than half the rotation rate. Okay, so Nick was right in the chat. Because there's no half here, this denominator is bigger and it's drops by more than 50%. So look at this. It was about 1 and now it's about 0.35. So it looks like we lost about 2/3 or something. All right. So, and then while not always true, when things slow down, usually energy decreases. That's not always true, but that's true in this case. All right. And so if you wanted to get the change in energy, so if we're trying to change in energy, we could get the final minus initial over the initial. And let's check this out. So doing the math, I have E final minus E initial. Take a second to actually follow through this crap. And this is a cool trick. By rewriting the final rotation rate, excuse me here, let me get this bigger. By rewriting this final rotation rate this way, by rewriting the final in terms of the initial, notice what happens. When we do this, all the halves drop out. And then this one, after we do this, all the omegas are going to drop out because there's an omega squared on each term. And so it cleans up dramatically. It looks like it's going to be horrible, and most of these take this form, okay? And so then, whoops, here's the final result. We lose 33% or lose 67%. So notice the change is negative 67. That's the same thing as losing 67. So you don't lose negative 67. So I'm going to put that in the chat just to make sure. So just to be clear, you don't want to say you lose negative 67. Got it? Don't say lose negative 67. You lose 67 or you change by negative 67, but don't say the lose negative. All right. So I'm going to tell you right now, here's something. Maybe you're tired. Maybe I've been doing a bad job, but try to listen to this fact, okay? One of the most common things students do in this problem that drives me crazy is they'll say, I see this problem. I'm going to do it with conservation of energy. I know it's got some initial energy. I know it's got some final energy. I'll just set E initial equal to E final. However, we just saw E initial is not equal to E final. So you can't do this problem with energy. That doesn't mean energy is lost. Where does this lost energy go? What force is doing the work, right? So clearly we know that E initial plus work equals E final. That is true. The problem is we have work being done here. There's external or work here. What is or there's work being done, non-conservative or external. That's a big hint. Remember, it's either non-conservative or external. So let's see. Friction is correct. So think about this. When this thing drops, initially it's not rotating. Friction is what gets it up to speed. So there's friction acting in here. This friction is what causes this one to speed up. And now friction, you might say, isn't friction an internal force? Yeah, but it's not a conservative one, which means the work done by that friction, right? The bottom turntable is actually displacing relative to the upper one, right? Because they're sliding, and only once they reach the same rotation rate will they stick together. So because there's that slipping going on, there is actual displacement between them, and there is this external force, or you could view it as external, but I should say non-conservative. So here in this case, that's what causes this. Let's check the chat question. Yeah, and it's during a very brief period of time. So does anybody know a practical application of having these two disks come together and come to the same rotation rate? There's still work done, Eston. Still work done. Yeah, a car. Yeah, sure. I'm thinking of something else in a car. I guess I'm thinking of a clutch, right? So this is one way you could have two disks come to the common rotation rate, and the friction causes them to come together. Now, in the brake pad, it's not quite the same because a brake pad stays fixed and something grinds against it. So it's similar, but a clutch, what you do is you actually have two circular plates come together, or something similar, a little different. But if you want to, you could look at a video of how a clutch works and you could learn that, and that's cool. Great. So yeah, there's a practical application. So if you don't drive a stick shift, I guess you never worry about that, right? You just hope somebody fixes your transmission, and that's what I do too. I don't know how to do it, so that's cool. It's a good skill to have, but I don't have it. All right, let's go on to the next one. So okay, 11.6 now. Yeah, right. It's the kind of thing that if you have the time and work on it, it's cool. Kind of like baking, right? Baking is torture for me. It always seems like a good idea, and then, oh yeah, it's a lot of work. I like going to the bakery more. All right, so let's go to 11.6, formation of a neutron star. So this is kind of cool. Okay, you have a star that's rotating with a period of 30 days. So once every 30 days, the star gets around. So it's taking a long time to rotate, 30 days. And now what's going to happen is we're going to say this star collapses from a radius of this to this radius. Think about that. That's crazy. Think about this, 3,000 meters. Think of something that's about 3,000 meters in size, right? That's about 2 miles. It's, a little bit bigger than Allen Hancock College, but not outrageously bigger, right? That's kind of, yeah, maybe like 3 times bigger than Hancock. So imagine a giant star collapsing down to like a couple of Hancocks. All right. Where'd that chat go? I lost it. Oh, there we go. Yeah, it's crazy. So, and these numbers, I think I actually looked these up. I think this might have been the sun's rotation rate, and this might have been a common size. So you could look that up if you want. Yeah, one one Hancock. All right. So now we're going to do this. First, I want you to relate period to angular frequency. So watch out for this. Angular frequency, angular velocity, usually those are the same. So I want to be clear about this one. The whole point of this part A, this is an important one. There's three things. There's F, which is frequency. So if you see me say the word frequency, I mean F. There is omega, which is angular frequency, or sometimes we call that rotation rate, right? That's the other term. And I want you to think RPMs. So omega is like the RPMs, but the word is rotation rate. So some of you answered period on the last test, but I kind of let that slide if you got the work right. And then obviously the last one would be period. And that's the time to complete a cycle. So just be aware of these words, all right? So now in our case, I think you know that omega equals 2 pi f, or 2 pi over the period. So we've been using this one a couple of times, but now I really want to point out, you got to know all three of these. This is on your exam equation sheet, but you should have this locked, all right? You got to know this, memorize this forever, all right? Memorize that. It's just so convenient in so many terms. Basically, we want to be able to use rotation rate, frequency, and period interchangeably. You just got to be able to do that, all right? Okay, so a period. So notice if we just flip this, that's pretty straightforward. Let's go over there and just double check. There it is. So omega is that. So this is what we've got. And then let's go read the question. Let's write down conservation of angular momentum instead of period. And now I will get to the chat in just a second. This is a rotating object that changes its shape. So I'm going to use this method now. So if I have a rotating object like a figure skater that brings her arms in or something like that, or a planet that collapses, we're going to use this style. So here's the equation. Whoops. So we got this. And then all I do is I plug in the period. And now this is going to be convenient. I've rewritten the conservation of angular momentum equation in terms of period. That way, if I want to use the period that was given to me in the problem, it's really easy to flip it around and say, oh, well, if I know the final moment of inertia and the initial moment of inertia and the initial period, I can find out the new rotation rate. Again, if I know these things, it's easy to get that. All right, and I'll get to the chat in a minute. And to be clear, I think that's what we're trying to do, determine the new period and the energy change, all right? So we're going to do the new period and the energy change, parts C and D. Let's go take a look at those. So the new period, it was a sphere. So I had 2/5. It is a sphere, has the same mass, it's the same same star, but now there's a different radius. This one's final, this one's initial. So I clear up all the crap that changes. Notice this cool technique. Now I don't have to convert all my junk. So by converting the equation, I don't need to convert my numbers. Look at this crazy thing. Look at that. It went from rotating once every 30 days to 4 times a second. That's insane. All right. Anyways, that's crazy. All right. Yeah. Okay. Oh, period's not in that. Yeah, that's right. So, okay, yeah, you just got to know this one. It should be on the equation sheet. Let's see. Oh, that's weird. That's all right. It's so important you should memorize it anyways. I could have sworn that was on there somewhere, but I don't know where it is. But yeah, memorize it, okay? So yeah, memorize that. All right. Okay. Good point to know. All right. So hopefully that's interesting to you. So yeah, and so all right, good enough. Let's go ahead and stop that. So if you have any questions about that, cool. Normally I would do 11.7 in class, and this is the classic figure skater demo, right? So yeah, I we can't we can't do this with a student, but you've probably seen this before where you start with your arms out and then you bring your arms in and you speed up, or the figure skater on the ice skates. And the idea is you had a large moment of inertia with the mass far from the axis, and then when you bring it in, you've reduced the distance between the masses in your hand and the axis, so your moment of inertia drops. And surprisingly, it only takes a tiny change to make you want to puke. So if your moment of inertia goes down even just a little bit, you start spinning slightly faster, but it's enough to make you want to puke. It's crazy. So a cool thing was yeah, that's right. That's right. Oh, here, let's see how I do. Oh my gosh, I'm gonna puke. Oh my gosh, I'm gonna puke. Okay. Anyways, yeah. It works a lot better if you have the weight. Um, one fun thing I did was my boss at the time, we had this all staff meeting where everybody has to go. It's kind of like, anyways, but I brought up the administrators, and I had the administrators versus faculty challenge. And I just spun him so fast, and then he had to call in sick the rest of the day. It was great. Simple pleasures. All right. So, yeah. All right. Let's keep rolling. Let's keep rolling and do another problem. Oh, let's go this way. Sorry about that. Okay, so if you're curious, if you need to skip a problem, skip this one, okay? Skip it. So skip 11.7. Skip 11.7. Hey, this looks like something worth noting. The all caps. Yeah, I know it's shouting at people. I wanted to shout at you. Do not use conservation of energy on an angular momentum problem. If you do that on your next test, you get 0 points on that problem. Got it? If you use conservation of energy inappropriately on an angular momentum problem, you get a 0. Just telling you. All right. So it's pretty important. We should go back here on this problem. Notice the energy changed. So I'll let you guys look that up on your own, but you can figure this out. And in this case, the energy change, speeding up, it's probably positive. And you could think, what force did work? And then, yeah, I'll let you read that one. It's actually pretty interesting. In theory, you could actually do 11.6 with conservation of energy, but you'd have to know how much work was done in collapsing the star. And that's not easy. It's so easy to do this problem with angular momentum. It's nearly impossible to do it with conservation of energy because you'd have to calculate the energy using calculus. It's a much harder problem. And I'll check what the chat question was. Maybe if my chat ever pops up. All right. Oh, there it goes. Yeah. All right. Good. Okay. All right. This one, we actually did one like this already. This was an old test question, and then people had trouble with it. So I'm going to let you do 11.8 at home. All right. I'm going to let you do 11.8 at home. It's a good test to see if you remember what we just did. Okay. And then, oh, I do want to talk about this one now. So let's look at 11.9. Okay. 11.9, this is kind of one of the last variations, all right? One of the last variations on this topic. All right, so let's look at this one. Mass M, speed V. I know that this thing has length D. Initially at rest. Okay, got it. All right. So think to yourself, which of these apply? Because if you can't get that, you don't know what equations to write, you don't do well on the next test. Okay. So this is, you got to get this step. At this time, it's okay if you guess wrong, but that's what the last 4 pages of this chapter are for. All right. So hopefully you've had a second to think. In this case, energy does not apply. When the clay sticks to the rod, energy is lost. Some energy goes into there. That's your standard momentum. And it turns out this applies and this applies. Wait a minute. Wait a minute, Mr. Jorstad. Didn't you say just a minute ago that we couldn't use this one? Didn't I tell you this was a no-go just a minute ago? And now here I am telling you it's okay. Why is this one okay to use both and the last one not? So if you want, open up your book to the 11.3, and I'll keep this on the screen for a minute. Look at 11.3 in your book and compare it to this problem. I'm telling you the truth when these two are both okay and this one's not. What is the difference? In 11.3, we couldn't use this. In 11.3, we couldn't use linear. Nope. Pivot, correct. Look at this one. There's no pivot up here, right? If there was a pivot up there, the pivot exerts an external force that causes momentum to not apply. Got it? So if you learn one thing out of this little problem, it's that, hey, all right, okay, got it? It's not perfectly elastic. So in this case, they hit and stick together. They hit and stick together. That's perfectly inelastic. Elastic means energy is conserved. And so I'm going to let me see if I have my chat here. So energy is conserved if you think of the entire universe and the energy inside the molecules of the clay, but we can't compute that. So because we can't measure the energy that was lost inside the clay, from a computation standpoint, we can't do conservation of energy here. All right. So watch out for that one. All right. And then because no pivot, or if there's a pivot, you can't use that. If no pivot, and then let me see. And then, yes, if you knew all the thermal. So let's say you had a way to very accurately record the temperature of the clay during the impact and could measure that heat loss, you could actually use conservation of energy. Yeah. So let me read this one. Sam's question is tricky here. If it was not in space and the rod was just standing on a table, in that case, you could probably still do conservation of both. So, Sam, let me see if I can make sense to you here. So remember, there's also this weird trick of if the external forces are negligible or if the external torques are negligible. So imagine, let me see if I could set this up. Here we go. Right? So in this case, whoops, if I came in here with a lump of clay and hit this thing, you would expect it to not only twist, but also go flying backwards, right? And so if you had a point particle come in here, geez, sorry, it's a lot easier with actual clay in class, right? Okay, sorry, give me just a second here. So the point particle comes in, hits it, it's going to pick it up, it's going to translate this way. And yes, there's a force from the table, but it's negligible. And so it's going to start flying off like this. And so you could actually use conservation momentum even if it was sitting on a table. Or what if you had a top view and it was sitting on it like this, and then you hit one side and then it would slide off like this across the hockey rink. So it would be both translating and rotating. And so you could use both that way. Did I address your question, Sam? And remember this, when doing conservation of angular momentum, so when doing for collisions, when you're doing this for collisions, we're talking about just before and just after. So in this scenario, right, when you have this thing coming in here, I would do a momentum problem for just before it hits it, and then just after it hits it. And then after that, you could do projectile motion, energy, kinematics, because it's one blob. So again, you do the momentum stuff just before and just after, and then the rest you do with energy or some other technique. Got that? So to finish that chat, when you're doing L initial and L final, use just before and just after. And then you could do like, because you're saying, wouldn't the rod fall down, blah, blah, blah. And that's true. So then you would have to do a 2-stage problem or a 3-stage problem or something. Okay. Okay, good. All right. Let's go look at what we were doing. I forgot what we were doing. Okay, got it. All right. So now we've got this part. That's a big deal. Let's look at this one. Okay. Think to yourself why the center of mass is relevant. All right. And if you don't know, I'll tell you in just a second. Okay. I'll get a sip of water. All right. This is something you may not know because normally I really focus on this in lecture and class because I could throw things around the room. But in this case, in case you didn't know this, we'll describe it this way. Okay, so we know that this is 2m, right? So there's mass 2m. This is mass m. So I'm going to guess that the center mass is probably about right here. And that will be the point that this object rotates about. So this is kind of cool. The center of mass will translate this way. And then on top of it, we get this rotation. So this will be V final from the momentum problem. And this will be omega final from the angular momentum problem. All right. And so why is it relevant? Hopefully this makes sense. If you have an object in free space, which this one is, in free space, deep, far from planets and anything else, it will rotate about its center mass. If you don't believe me, take something weird that's not going to injure someone, that's got a weird shape. I would use like big pieces of foam, or you could cut out a weird piece of cardboard. And what you could do is you could find the center of mass by bouncing a bright sticker on it and then throw it across the room. And you could see that it actually rotates about that spot. That's what we got. So, all right. Anyways, so that's why that's relevant. And then this is a weird one. Look at this. Read this carefully. The moment of inertia about the rod and clay system about the center of mass of the system happens to be 1/3. That's a pure coincidence, right? Think about this. This one right here is a 1/12 2m. And then I'll let Trey get the chat. D squared, right? So that's a 1/12 2m d squared, which is 1/6 m d squared. Now, if we have the center mass being right here, the distance between here and here is how much? Probably, let's see, this is d over 2 and 1/3 of that. I think that's 1/6 of d is the distance. So notice this distance right here would be 2/6. I'm sorry. Yeah, 2/6 or 1/3, I think, if I'm not mistaken here. So let's write that. Let's double check that in the book here and see if I'm screwing this up. All right, so, and I'll get the chat here on the way. Okay, if the mass is in the wrong. Yeah, exactly. Yep. So if you had like a really tiny bullet that has negligible mass, you could think of it as negligible. So yeah, I agree. Okay. Let's go over here and take a look at this one. Whoa, that's a big font. What problem are we doing? 11.9. And we have another day to work on this, people. So just so you know. All right. So there's that. There's this one. And so look at this crazy center mass calculation. You'll see that we use this center mass all the time. Hopefully this makes sense. Follow this calculation. This is a non-trivial portion of these rotating problems, okay? Okay, look at all this and give it a second. I want the total clay rod moment of inertia about the center of mass, so about the green X. So I need the rod about that and the clay about that. The rod is a one, there it is, and then you have to remember to add in this parallel axis theorem crap, parallel axis theorem. And then, okay, that's good. And so, and then notice for the point mass, that's pretty straightforward. When you add it all together, you get 3/9, which is 1/3. It's crazy. Let's just check this out. Using conservation momentum, it's actually really easy. MV was the initial one. Afterwards, it's got mass 3m. So there's the translational speed. Here's the here's the angular momentum calculation. Piece of cake. There's for the point mass, I use this formula because it's easiest. In this case, R perpendicular is d over 3. Remember, let me go back to the other page so I can draw it. Remember, the center of mass is right here. And so this distance is d over 3. So that's where I got the impact parameter. That is R perpendicular, the impact parameter. All right. So when I go back to this one, maybe, if you're wondering, that's where I got R perpendicular is d over 3. Here's the moment of inertia. You can get this final, how funny. It's just V over D. That's crazy. And then you can do all the rest of this stuff and you're good to go. And I think that's pretty good for today. So I want to stop and see if there's any questions. Woofda. What do you think? Probably need to work with it a bit, right? It's probably still pretty new. I'm just pausing to see if you guys have any questions for me. I'll let you take a look at that one. I'm going to try and bring up a link really quick and just share a link with you that you can see. Ugh. I don't know if, yeah, let's see. This is a fun link. So this is, if you look at, so if you look at that video clip, the two problems, 11.10a and 10b, to be honest, you could maybe look at those problems, but not try to do them all. Maybe like read the solutions. So I would say maybe read the solutions for A and B after watching the video rather than actually doing all the boring math. But if you want to, you could do part A is pretty, yeah, it's just kind of interesting. So if you want to, you could take a look at part A of 11.10b. That's a look at 11.10b part A. That's a weird problem. But the question is, if you shoot the bullet off axis, will it go higher or not as high or the same height? And that's what that video shows you. And so you can watch the video and make your guess. And it's linked to these two questions. And I kind of ran down the math for you if you're curious. So, all right, let's see. Gotcha. And so, yeah, okay, that's cool. I'll stick around here for a minute if anybody has any other questions. I'm going to end the live stream right now.